So as I'm looking at this one, guys, okay, and it says we're going to test the claim that the majority of adults prefer window seats. I heard a lot of people talking about that. Like, how do you express that? And remember that this section 8.3, okay, is hypothesis testing about a proportion, or for a proportion, or a percentage. And so the claims are going to be about p, little p. Remember, we talked about big P yesterday, but this is little p. And so you're going to see I'm going to write little p here, and I'm going to write little p here. That's what we're dealing with in this section. Okay? And when I say majority, I'm saying that the percentage should be bigger than what? 50%, right? If it's equal to 50%, that's not a majority. But if it's bigger than 50%, that's a majority. And of course, you know, some people are asking, well, I heard Laura say, well, what's a majority, right? Like in law, right? Say you're talking about the Senate, and you need a Senate majority, you need a 2/3 majority or 3/4, depending on what it is, right? Now, this is 50%. Hey, guys, did I write down equality or not? No. If you write equality, that's different than if you don't. Because which one of these two contains equality? The null is always going to be equal. And so where does this original claim go? The original claim, because it doesn't have equality, the original claim is going to go down here. And it's going to be the alternative hypothesis. All right? I'm going to say P is greater than 50%. And my null hypothesis is going to be P what? P equals 50%.
When we talked the other day, I thought we had said that the alternative hypothesis was always the opposite of the original.
So that's interesting. Some of it depends on your book. Okay, I'll be honest with you. But I guess what I said the other day is more old school. All right? But if you follow our book's convention, which is, I think, more of the standard convention nowadays, we're going to always have equality for H naught. Okay? I mean, just to kind of go on what I would have been, say, when I was raised learning statistics, what we would have done is, again, this does not contain equality, so I put it down here. And you'll see some people would write this. They would write P is less than or equal to 50 is the null hypothesis. But in some ways, that doesn't really make sense. I mean, the null hypothesis is when you're testing P equal to a certain value. So I would like to stick with this convention. We're always going to put equality for the null hypothesis.
Yeah.
If this contains equality, we're going to treat it differently than if it doesn't. Here it doesn't, so I'll make it the alternative.
So I guess just like how do we determine then?
You'll have to see another example or two, and I'll come back to that question.
Okay.
Okay? I'm trying to explain it. It's because there's no equality here. It's the alternative.
And you'll always use the same number in all three of them?
Oh, yeah. Yeah, we're not going to change the number. That's important to understand. Use the same parameter P and use the same number for these claims. Jared, again, to say this, what's important here is, do we have a one-tailed test or a two-tailed test?
One-tailed.
That you know. How do you know? Because you're looking at the sign of the alternative hypothesis, right? When's the only time you have two-tailed? If that says what? Not equal to, then it's two-tailed. This is a one-tailed test. That's going to make a difference. You're going to see it's a little bit different than some of the ones we did yesterday. Okay? So we need our test statistic in a moment in order to do this. That's kind of the next step. It says we're going to use a, bless you, 0.01 significance level to test the claim that the majority prefer the window seat. So, you know, since we have a one-tailed test, I guess I'll draw it. You know, it's kind of like this, right? And this is, you know, the z, where the mean is 0 and the standard deviation is 1. And when they say we have a 0.01 significance level, What is that? That's alpha. So my picture is this, guys. Alpha is 0.01. And remember how I said it's important to understand that this is one-tailed? Where's the tail? Yeah, the tail is over here on the right because it's greater than. It's kind of cool because it's like a little arrowhead. It points where it's going to be, right? This has an area of 0.01. That's important to understand. It's a one-tailed test, so that's 0.01. Guys, if it were a two-tailed test, a couple things would happen. First of all, I'd have two tails. But secondly, what would be the area of each of the tails in that case? 0.005. That's right. It would be 0.005. Who's with me so far? Okay. So now, the next thing to do is let's compute the test statistic. The test statistic, and again, you'll have a formula sheet, right? But here it is, right? It's going to be p hat minus p divided by a big square root of what?
Q over N.
Yeah, we've seen this before. P times Q over N. Okay? So that's the test statistic that I'm going to be using here. So let's see. P hat. Do we have P hat? Or can we compute P hat? Maybe that's the question, right?
492 minus 600.
Yeah, because they say there's 806 adults asked and 492. Yeah, so I agree. We're going to have to type that in, right? Here, to get P hat. And again, just so everyone can see what I'm saying, right? 492 of them chose a window seat out of the 806 adults. So let's type that in. Actually, maybe I make this a little bit smaller, be smarter. No, didn't work. So this is going to be 492. Oh, it's not typing, guys. Okay, we'll try that again. 492 divided by 806. Did you guys get 0.61? Yeah. So 61%, right? Okay, I'll write 0.6104 for P hat. So we compute P hat is 0.6104, and that's what's going to go there. So I have Z equals 0.6104 minus 0.5, because that's what we're saying P is, right? The null hypothesis tells you what to put in for P. Over square root of, and what do we have? We have PQ would be 0.5 times what? 0.5, because Q is always 1 minus P. Right, they have to add up to 1. All over N, and was N 806, I think? Yeah, 806. Okay, so I'm going to try and type that stuff into the calculator.
How do you get the 0.5 again?
Well, I guess because, I know that P is 0.5, right? And Q is always 1 minus P. So it's 1 minus 0.5, which is also 0.5. Sometimes the proportion is going to be something else. And then we'll have to subtract from 1. And I guess the first two examples you've seen have been like this. So let's compute Z. So let's see. If I go to the calculator again, well, I can type in, open parentheses, this thing, 0.6104 minus 0.5. I like to put that in parentheses because that's the numerator. divided by, and now we need the square root key. So try this, guys. Hit your second x squared. I hope you guys are trying this as I'm doing it, because I think you'll get more out of it if you do. And then what are we going to do? We're going to type in, well, 0.5 times 0.5, and then divided by, what do we have? 806. So I got to, ooh, is that a big z value?
Big.
That's huge, right? I mean, where is that on the map? My z value I just computed is equal to, we're saying, 6.26. Wow. Here on the picture, that looks where? If your z value is 6.2, remember the roller coaster hump, that's 1 standard deviation, right? We're talking way over here, right? That's my z value. And I guess I'll say a few more things. Since the z value is in the critical region, what do? We reject what? Let's be careful about what it is we reject. There's only one thing you can either reject or fail to reject, and that is the null hypothesis, H0. Okay? But you're not done. If you guys walk out of my class and that's all you know, then you're not doing statistics yet. Statistics is solving problems, real problems. And the question is it true that a majority of people prefer a window seat? Based on this data, right. So, our data supports, because here's the thing, guys. The reason I said supports is why? Because if you reject the null hypothesis, then you're supporting the alternative hypothesis, right? This alternative, which like Laura said, that's the same as the original claim, right? So it's funny, if you want to support something in statistics, what you have to do is you have to kind of rig it so that that's your original claim and it becomes your alternative hypothesis. Then you might be able to support it. Because our data says, is there any way that P equals 50%? No. I mean, look what our P was. Our P was 61%. Are you with me? There's no way that this P is 50. Because I surveyed, it's not like I just surveyed 2 people. I surveyed 806 people. That's what N is. And so our data supports the claim that a majority of customers prefer the window seat. You guys, some of this, what we're learning is just language, you know? Our data supports the claim. Yesterday, I think the last example you guys saw, we had a fail to reject. Do you remember that? This one was where we rejected the null hypothesis. If you go back to what I did yesterday when I failed to reject, let's find it. Was that the luggage problem? No. Here. This one was all about, right, this was the two-tailed test, and we failed to reject. And look what I wrote. There is not sufficient evidence to say anything. So if you reject the null hypothesis, you're saying, we kind of don't have enough. Okay? You either reject or fail to reject. Let's look at number 18. I think that'd be a nice problem to follow up with. Oh, before I do you guys have questions on what we wrote down? Once you identify those three things, then we'll bring it back up front, okay? So again, original claim, null hypothesis, alternative hypothesis. Talk to each other about that for a moment. Okay. We're looking at number 18. We'll see what you guys have. Original claim. What are you going to say about P here? I think it said P is equal to 43%, right? I mean, if you look very carefully, it says, yeah, test the claim that among all voters, the percentage who believe they voted for the winning candidate is equal to 43%, which is the actual percentage of voters for the winning candidate, right? So winning candidate took it home 43%, they're saying. Which means there must have been more than two candidates. Oh, yeah. Must be, right? So if you get this kind of situation, where does that go? Does that go at H0 or H1? Why does it go H0? This is important to understand. You have equals, right? So I'm going to write P equals 0.43. Okay? Which means, what is the alternative hypothesis in this case? And why is that important? Yeah, this is a two-tailed test, guys. And if you look at the problem, I remember they said we want to use what significance level? 10%, right? Alpha is 10%. And so my picture is this, right? I know that this is what I do, but because it's two-tailed, critical regions are here and here. If I get, like if my P, my proportion is really high or really low compared to 43%, I'll reject the claim that it equals 43%. Maybe not 44%. I don't know. We'll figure it out, right? But this is, oh, and since we know that alpha is 10%, what does that tell me about the picture? This is important because you're going to need it for the critical values. How much goes here? Just 0.05 here and 0.05 here, right? So how much is left over? This is 0.90. And you're going to have to work to get what the critical value is and compare it to your test statistic. So I'm going to pause, turn you loose a little bit, see what you can fill in. You guys have that formula, hopefully? The other thing we need, right? You have to look at the, so write down the formula, and then I'll put the data back up here, because we have to compute p hat, I think, right? So we'll see what happens. You guys can work on this a little bit and tell me, see if you can do the problem. I'm going to earn my pay. Let's see what happens here, right? So first of all, we need p hat. What did everybody get for p hat, and how did you get it? Well, let's see. P hat first of all, because I can't compute the z-score if I don't have p hat. Let's see. P hat is equal to x over n, right? What are x and n in this problem?
308 and 611.
I agree. 308 and 611. So I'm going to go ahead and type that in. That should be easy. 308 divided by 611. I thought Jamie had a good question. He asked me, well, how many decimal points should I use? I tend to use 4, typically, for a probability or percentage. So I'm going to write down that this equals 0.5041, right? So P here is 0.5041. By the way, if you didn't know anything about statistics, you might walk in and just say right now, the proportion we had in our study was about 50%. The original claim is what? That the proportion should be 43%. Are they close or not close? Well, I don't know. We'll see. We'll see. Maybe that's why we need statistics, because it's hard to answer. I had different answers here, right? So now z, we want to compute. I have this p hat, so I put that in the first slot in the formula. 0.5041 is p hat. So now I get z is equal to 0.5041 minus what? 0.43 divided by big square root of what? Let's be very clear here. In the formula, is this a p or a p hat down here in the square root? So what do I have to put? Okay, so let's put 0.43 here. What else do I put? It would be 0.57 because that's 1 minus p, right? These two should add up to 1. And if you add them together, you get 1. Who's with me so far? Can I see show of hands? That's outstanding. Divided by, do we know what n is?
611.
I'll trust you on that. All right, here we go. Now, I know I wrote it this way, but when I put it in the calculator, there is one thing I'm going to do a little bit differently. I'm going to have parentheses around the numerator because I'm subtracting. Otherwise, it'll mess up. Okay? So let's go ahead and type that into the calculator if we can. Type it with me because some of you said you didn't like your z-score. I want to make sure you know why. Here we go. So I'm going to open parentheses. I'm going to type in the 0.5041 minus the 0.43. I'm going to close parentheses. I'm going to divide. Now what do I type in? Yeah, and when you do that, it automatically opens a parentheses for me. Or it gives you this symbol, one of the two. And now I'm going to type in 0.43 times 0.57 divided by 611. Enter. There we go. My z-score, is it big or small? That's pretty big. That's pretty big. 3.699, right? So call it 3.7. My z-score is 3.7. The question you have to ask, guys, is does that put it in the critical region?
Yeah.
How do you know?
Well, because our critical region is 0.05, right?
Well,
And
the critical region has area like this. And I think you're right. I think 3.7 is around right here. Remember, this is a z-score. Z-scores are along the x-axis. It's not area, right? I think it is in the critical region. But there's two ways you can be sure if it's in the critical region or not. One way is to find the critical value. I think that may be easier. The second way is to compute what's called the p-value. The homework actually asks you to do both. So I'm going to do both here. The first problem, I didn't do the p-value. I'll show you why in a moment. So anyways, what is the critical value? The critical value, right? So let me write this. The critical value would be right here, right? Z alpha over 2. You guys should know how to find that, right? What function am I going to use on the calculator to find that z-score? You sure are. Because we have the probabilities, right? If you want a z-score, we're going backwards now. Inverse norm. Inverse norm of what? Look at the picture. What is it? I think I heard it. Well, I'm going to write 0.95 to get this one, right? If I did 0.05, you're right, I would get the negative critical value. You could argue there's actually two critical values for a two-tailed test. I'd be okay with that. I understand that, right? So I'm going to go ahead and type in inverse norm of 0.95. Calculator. So let's see. Second distribution, choice 3, inverse norm of 0.95. I think I've seen this one before. The z-score is 1.645. Have you guys seen that one before? Not as much as 1.96, but we've seen it before. Z alpha over 2 is 1.645. So do we reject the null hypothesis?
Yes.
Why? 3.7. Our statistic is in the critical region, right? So let's finish with our conclusion. We reject the null hypothesis. Okay? And I told you we're not done. We have to say something about the original claim. The original claim was that P equals 43%. Do we believe that or no? No. I'm going to say this. I'm going to say there is sufficient evidence. Why do I say there is sufficient evidence? Because we're rejecting the null hypothesis. That's what you can do if you have enough evidence. There is sufficient evidence to reject the claim that the proportion of voters. See, now, to write the rest of this, what claim? You kind of have to go back to the text. What did the text say? It said, test the claim that among all voters, the percentage who believe they voted for the winning candidate is equal to 43%. So the claim that, maybe the easier way to say it would be, 43% of voters believed they voted for the winning candidate. That's weird, actually, if you think about it. Right? I mean, it's a fact that 43% voted for the winning candidate, but if you ask them, they're going to say, oh, there's a lot of people that think they voted for the winning candidate when they didn't. Yeah, well, it's interesting. It's very interesting, I think, what that data shows. Do you guys have questions so far? Yes, Sarah.
So how do you know if you reject it or not?
The reason we reject it, that's a good question. Why do I reject the null hypothesis? Does anyone have the answer to that right now? No? Well, then I'm in trouble, right? Okay. Why? So it's a very good question, Sarah, because we don't know yet. Because, so I'm going to write 1. Because our test statistic is in the critical region. Let me show you a picture again, right? What was our test statistic? It was 3.7, right?
Yeah.
Our test statistic was 3.7. Where was the very start of the critical region? Well, that's the critical value. What was our critical value? 1.645. I guess also you have another one on this side because it's a two-tailed test, negative 1.645. These are critical values, right? And so, do you guys see how 3.7 is clearly to the right? And so it's in the critical, it's in the tail. It's in the critical region. Are you with me? So if that happens, you know we reject H naught. Now, there is another answer to this question that Sarah asked also, and that's important for me to talk about now. Number 2, because the p-value is low. The p-value. And I want you to understand what p-value is. We mentioned it yesterday. P-value is the probability of being at least as extreme as our test statistic. Oh, this was a conditional probability. Given that what? H naught is true. You guys, I know we wrote it down yesterday, but this is what p-value is. The probability of being at least as extreme as our test statistic given that H naught is true. How do you compute the p-value? You have to do that on the homework. Here's the picture. Ready? You draw the bell curve. You plot your test statistic on it. That's way over here, right? It was 3.7. Now, when I say at least as extreme as 3.7, that means if you have like 4, that would be more extreme, right? Anything over here, I want to include. But I also want to include, see, negative 3.7 is just as extreme as 3.7, right? Because what's the mean? The mean is 0. So anything over here, I also want to include. The p-value is, remember, p stands for probability. The p-value is the area of this blue region. How do you compute that area? Well, to get that area, the p-value will equal, you know what I'm going to use? Normal CDF of what? How about we go from 3.7 as my lower limit to what? 10 is good enough, right? But then I have to do one more thing. Because this is a two-tailed test and we have to get both areas, we have to do times 2. 2 times the normal CDF of 3.7, 10. So I'd like to compute the p-value for you because that's something else the homework asks. Ready? Let's type in normal CDF of what? Lower bound? 3.7. Upper bound, something big. 10's good enough. I'm going to paste that in. Oh, what does that mean? Tiny, tiny p-value, right? Oh, but that's not the p-value. I still have to do what? All right, let me multiply by 2. It's still going to be really small, guys. The p-value is 2.156 times 10 to the negative 4, right? So the way you would write that, if you wanted to use regular notation, right, it would be 0.0002, right? 0.0002. Would you agree that the p-value is low? Then the null must go. If the p-value is high, we let it fly. We fail to reject. But if the p... How low does it have to be? How low does the p-value have to be for you to reject H naught? This is key observation.
than the significant?
Yes, it has to be lower than the significance. So for our problem, and boy, that's way up here at the top, the p-value has to be lower than 10%. And it is, right? It's 0.0002. It's much lower. So this one we're clearly going to reject, the null hypothesis. But when you're making that decision, sometimes it's easier just to look at the p-value. Sometimes it's nicer to look at a critical value. You guys should definitely be familiar with both techniques. And that's why the homework asks you to do both. And I'll do the same. I'll ask both kinds of questions. What's the p-value? What's the test statistic? These are things I'll ask on the quiz on Friday. Okay? Maybe we can do it now. Let's take a peek. Amy and Jamie, what was the first one you wanted me to go over?
13.
Oh, it was 13. But Kelsey, you had a question on which one? There was one of those. Was it 7? It says, for each of these, do the following. Express the original claim in symbolic form, identify the null and alternative hypothesis. I think we could do this now, right? So for number 7, what would you write as the original claim now? First of all, you guys aren't going to use the letter P, are you? What are we going to use? Don't say sigma, don't say sigma. Mu. Mu is, right? The original claim is about the mean. So the original claim for number 7, this is section 8.2. Right? I mean, it's kind of the same deal now, right? We're going to go, for any of these problems, we're going to go original claim. We're going to go H0, and we're going to go H1. Can you guys do this now? Let's see. Original claim has to be with the mean. Mean is equal to what? The original claim, oh yeah, it says 76 or lower. I guess I don't want to use equals for the original claim. How would you write that? Not P. Not P. We want mu. But I'm saying I don't want equals. I really want, when it says 76 or lower, wouldn't you guys write less than or equal to? That's 76. Less than or equal to is 76. So that's kind of interesting because does the original claim contain equality? I guess it does, right? It says less than or equal to 76. So that kind of belongs here in H0. And what am I going to put for H1, the alternative hypothesis? We're going to do the opposite, yeah. So we're going to do the opposite of this. We're going to say mu is greater than 76 is going to be the alternative. Because the original claim, when it contains equality, we're going to kind of put that into the null hypothesis. We're going to say, but when we write the null hypothesis, what are we going to write? We're going to write mu equals 76. Notice there's no decimal points here because these are means, right? 76 what? What are we talking about here? This was, your pulse, so beats per minute. And then it says, for the random sample of adult females, the mean pulse rate was 77.5. So you could ask, is that different enough from 76 that it skews things? I don't know. These are kind of things we could test. Okay. 13, Jamie, is that what you guys said? 13. Here we go. Find the value of the test statistic. Of course, now you know this formula, right? In and out. Oh, wait a minute, though. Is this one about a mean or a proportion? Number 13. Yeah, we do have to identify what's going on here. 13. What kind of parameter are we testing here, guys? What's the original claim? Let's start with that. Number 13.
P equals 0.75.
I agree. The original claim for 13, it says P equals 0.75. It says 3/4, right? But I know that 3/4, right? I know that 3/4 is the same as 0.75. Okay. Do we have P hat? Yeah. I mean, for this one, we're going to be doing Z equals, again, P hat minus P divided by square root of PQ over N. And I think you should be able to fill in everything based on what we've seen today. I want to talk about 15 for a second, just to show you, because as I look at it, I think that could be a little confusing. When you look at 15, what is the claim? Ha. What is it that they're talking about that equals 5? Standard deviation, right? The original claim this time says standard deviation equals 5. Now, I mean, I could see writing this, but there's actually a symbol. What's the symbol for standard deviation of a population? Sigma equals 5. That's right. That's the original claim. Now, I will tell you, we talk about this in section 8.5. I am not going to, on Friday's quiz, give you any problems where you have to do the standard deviation. I'm not. But you have to do this homework problem. So how do you do it? Well, let's go to the formula sheet. There's a reason I punched this up, right? And if you scroll down, there it is, right? Standard deviation or variance for one population. Look at that, it's test statistic. You might not know how to read that one, but we're going to use it later in the course, so I'll mention it now. It's called the Greek letter chi, and that's actually called chi-squared. Has anyone ever heard of a chi-squared before? No? Anyone going into either biological or health sciences? You will. You'll hear of chi-squared. Chi-squared is a really important distribution in those applications. So chi-squared, it says, is equal to n minus 1 times s squared over sigma squared. And I guess the question is, you know, when I look at that formula, so I wrote down the formula, right? Can I fill things in? Well, I guess at least I could fill in this, right? Sigma is 5. And now you would have to look. I bet we know what n is. Do they give you s for number 15? I better look at it. I can't remember. Do they give me s? Random sample, there's n, 40. Oh yeah, they give me s's, so you can do it. You can do everything you need. So that's good. Is statistics a good insomnia treatment? No, you guys are awake. I don't know. Anyways, that's not what it says. It says we have this huge, you know, when I get this huge kind of problem right here, I don't want to be intimidated. The first thing I'm going to do is try and figure out what is it asking. So I'm going to go to the very last sentence. This. See how it says test the claim here? or it says the question mark, assume that test the claim that after treatment with what's it called? Zopiclone? All right.
Oh,
You know this?
that's, I mean,
Zopiclone, did I pronounce it correctly? Subjects have a mean wake time of less than 102.8 minutes. Oh, they're saying that's how long they're going to stay awake? 102 minutes. That's a long time, right? Does Zopiclone appear effective? Oh, I see. So now that I have that, I go back and I read a little more. Before the treatment, 16 subjects had a mean wake time of 102 minutes. After they took Zopiclone, the 16 subjects had a mean wake time of 98.9 minutes. Right? So it went down. Assuming the 16 sample values appear from a normally, test the claim that after treatment, subjects have a mean wake time of less than 102.8 minutes. Right? So I guess here we are in section 8.2. I'm going to start on a new page. And we're going to pick up this example tomorrow. But I will say this. When you do your original claim, the original claim is going to be mu, not p anymore. And we're testing the claim that mu is what? Look at that last sentence. Mean wake time, less than 102.8 minutes. Less than 102.8 minutes. Okay? So this is number 18, and I think I will start with that tomorrow. Help you guys start getting ready for that quiz. All right, guys, have a good rest of your day.